Hello, dear friends. I am Dr. Shailesh Palekar. I am working as an associate professor in the Department of Mechanical Engineering, Sanjivani College of Engineering, Kopargaon. This is our 18th lecture for the subject Dynamics of Machinery. In the previous lecture, at the end of that lecture, we have discussed that based on the value of zeta, that is damping factor, we can classify the vibrations in three different types, that is overdamped vibration, underdamped vibrations and critically damped vibrations. In this lecture, we will derive the equations for finding the displacements in all these three types. So, we will start with overdamped vibration or overdamped systems. As per the definition, the, the overdamped vibration can be explained as if the damping factor zeta or xi is greater than 1 or the damping coefficient C is greater than Cc, that is critical damping coefficient of the system, then the system is said to be overdamped. Mathematically, for overdamped system, we could write zeta greater than 1 or C is greater than Cc. Let us call this equation as equation A. Then in overdamped system, the damping is comparatively large. As the name indicates, overdamped means the damping is more or comparatively large. As we have discussed in the previous lecture, the two roots of the equation of equilibrium or fundamental equation of motion for the damped system, we got the two roots as S1 and S2, and they can be given as S1 is equals to minus xi plus square root of xi square minus 1 close this bracket multiplied by omega n, and S2 is equals to minus xi minus square root of xi square minus 1 into omega n. Let us call this as equation B. In this case, the two roots S1 and S2 are real and negative. What is the meaning of this? That these two roots, if we put the value xi greater than 1, that is, suppose let us say 2, the value of xi is 2, then minus xi plus this, if you put the value of xi in this equation, then you will definitely get that the value is real and it is negative. So hence in overdamped system, the solution to the differential equation, which is given as x is equals to a into e to the power minus xi plus square root of xi square minus 1 into omega n into t plus b into e to the power minus xi minus square root of xi square minus 1 into omega n into t. If you remember in the previous lecture, we have the solution for the damped system as x is equals to a into e to the power s1 into t plus b into e to the power s2 into t. With that, in that equation we have put the values of s1 and s2, and we could write the equation for differential x is like this. So let us call this equation as equation number 1. The values of a and b in above equation can be determined from initial conditions as follows. Let us consider initially, that is at t is equals to 0, the displacement is capital X0 and velocity is 0. What is the meaning of this initial condition is? Let us consider take the example of pendulum. When we have to give the displacement initially to the pendulum, that time consider that it is at mean position. From that mean position, we have to pull or push that bob to one of the extremity. At that extremity, when you just hold it, you have holded it in your hand, that time you can say that at t is equals to 0, yet your motion has not started. So you can say that at t is equals to 0, your displacement is how much? That is the maximum value of displacement, that is you have displaced it to the maximum position that can be possible. So that's why we have written here that at t is equals to 0, the displacement is capital X0. Capital X0 denotes that it is the amplitude, maximum possible displacement throughout the operation. And at that time, you have still holded that bob in your hand, you have not allowed that system to perform the motion. Therefore we could write at t is equals to 0, velocity is 0. So these are what the initial conditions, that is at t is equals to 0, x, which is the displacement, and capital X0, which is the amplitude. X is equals to capital X0. Let us call this equation as C, and at t is equals to 0, x dot is equals to 0, that is velocity is equals to 0. Let us call this condition as D. Now from equation 1 we can again rewrite this equation as x is equals to a into e to the power minus I plus square root of xi square minus 1 into omega n into t plus b into e to the power minus I minus square root of xi square minus 1 into omega n into t. And if we differentiate this equation so that we get the value of velocity, that is x dot, then after differentiation we could write the equation like this: x dot is equals to a into minus xi plus square root of xi square minus 1 close this bracket into omega n into e to the power minus xi plus square root of xi square minus 1 close this bracket multiplied by omega n into t plus b into minus xi minus square root of xi square minus 1 into omega n into e to the power minus xi into square root of xi square minus 1 into omega n into t. So in these equations E and F we have to put the initial conditions. So at what are our initial conditions? That is, at t is equals to 0, x is equals to capital X0, and at t is equals to 0, x dot is equals to 0. Means in both these equations we have to put the initial conditions as it is. So when t is equals to 0, x is equals to capital X0, that is our equation C we have to put in this equation E, and D is kept in equation F. So substituting C in E and D in F, we get what is our condition C is, that is at t is equals to 0, x is equals to small x is equals to capital X0. So x is replaced by capital X0, and in all these both these terms we have to keep t is equals to 0. See, if we put the t is equals to 0, then e is equals to e to the power 0 becomes 1 plus b into e to the power 0, again it becomes 1. So we could write x0 is equals to a plus b, and our another initial condition is, that is at t is equals to 0, x dot is equals to 0. So to put the value of t and x dot in this equation F, we could write the equation like this: 0 is equals to a into minus of xi plus square root of xi square minus 1 into omega n plus b into minus xi minus square root of xi square minus 1 into omega n. Let us call this equation as equation G. From equation F and G we can write for a and b as a is equals to plus xi plus square root of xi square minus 1 upon 2 into square root of xi square minus 1 into x0, and b is equals to minus xi plus square root of xi square minus 1 upon 2 into minus square root of xi square minus 1 into x0. After solving equation F and G, we get the values for a and b like this. Now we have the values of the constants a and b to solve the equation X, that is the displacement equation. Okay, so we will substitute the equation H in our equation 1. We could write the equation as x is equals to capital X0 upon 2 into square root of xi square minus 1. In the bracket we have plus xi plus square root of minus xi square minus 1 into e to the power xi plus square root of xi square minus 1 into omega n into t plus in the bracket minus xi plus square root of xi square minus 1 into e to the power minus xi minus square root of xi square minus 1 close this bracket into omega n into t. Just what we have done, we have put the values of this equation H, that is a and b, in our equation 1, and we have just rearranged that equation. So we could write the equation in this way. Now if we use this equation for x, that is this last equation, that is equation 2, then the time displacement curve for the overdamped system can be drawn like this. We get the time displacement curve for overdamped system like this. In overdamped system, as both the roots are negative, that what we have discussed previously, the displacement x goes on decreasing with respect to time t. As the time increases for the vibration, then the displacement goes on decreasing. The motion represented by equation 2, that is our x equation for displacement, what it represents in overdamped system, the motion is aperiodic. Therefore, the system is non-vibratory. Once the system is displaced from the equilibrium position, it will take infinite time to come back to the equilibrium position. So when you displace the system from the mean position, and if the overdamped conditions are applied, that time what happens, as you relieve the force, the system gets that motion is aperiodic, means it will not repeat itself, but it will come to the mean position, will take some time, and after coming nearer to its mean position, it will take infinite time to come back to the mean position, exact mean position. That is the indication of this time displacement curve. That is, initially when we have given certain displacement to the system, it will move and it will try to come back, but it will never go down. Okay, this will we can say this way it will not perform the motion, but just in only for one cycle it will show all these things. So initially we have given the displacement, it will move to the extreme position, and from that extreme position it will start returning to the mean position, toward the mean position, but as soon as it will reaches nearer to mean position, it will take infinite time to come back to exactly the mean position. This is what the x indicates, that is our overdamped systems displacement equation represents. These overdamped conditions are normally used, or the system will perform overdamped type will behavior when the dampers are very old. For example, let us take the example of the door closer, the hydraulic door closure. You may came across so many times such situation that suppose your higher authorities cabin is there, and that to that door we have hydraulic door closure. So as soon as you push that door, when the hydraulic door closure is new, that time as soon as you push the door and you relieve the force, it will come back to the main position very early, or very as soon as possible. But if that door closure is old one and it becomes somewhat harder, that time when you push, for your pushing much more force is required, and as you push the door it will get open, but it will never come back to the mean position in a quicker time or very less time. Okay, so it will take much time, much more time, or we can say the time required is more to come back that door to the mean position. This is what the example of overdamped system. Now the next case is our critically damped vibration or critically damped systems. So how we can define critically damped vibration or critically damped system, as if zeta is equals to 1 or c is equals to cc, then the system is said to be critically damped. In such cases, the two roots s1 and s2 are given as s1 is equals to minus omega n and s2 is equals to minus omega n. Let us call these equations as I and j. I hope you are understanding that when zeta is equals to 1, means zeta is what we have, it is a damping ratio, and it is defined as ratio of damping coefficient to the critical damping coefficient. So we can write C is equals to Cc. In such situation, the system is called as critically damped system, and the vibrations are known as critically damped vibrations. When this situation arises, that time the two roots which we have seen in the previous slides, the value of those we can say the roots will be equal to s1 is equals to minus omega n and s2 is also equal to minus omega n. So instead of going into detail of the derivation for finding the x, as the steps we have followed in the overdamped system, that we have applied the initial conditions, we will keep the initial conditions as it is, and we will put the values of initial condition in the value of x and x dot equations, and we will find the values of a and b. After finding the values of a and b and putting those values in equation 1, we get the equation for displacement if for critically damped system as like this: x is equals to capital X0 in bracket 1 plus omega n into t close this bracket into e to the power minus omega n into t. Now if we plot the time displacement curve for this case, that time we get the shape of time displacement curve like this. As the name indicates, this system is critically damped, means still the damping is more. So when the damping is more, there is no chance of the system to perform the number of cycles. In a single cycle itself, the system tries to come back to the mean position and it will never move further in forward direction from mean position. Okay, so from equation 2, this equation x, it is seen that as time t increases, displacement x decreases. If you put the value of t in this equation, then definitely you will find the value of x goes on decreasing in each cycle or in as the time increases. Okay, and at t is equals to infinity, x tends to be infinity. Means to this indicates, this discussion can be further extended as that when we increase the time, if you look at the figure, then you can easily observe as compared to the overdamped system, in critically damped system, the system come back to the mean position, towards the mean position as early as possible, somewhat fast than the overdamped system, but it will never reaches to the mean position. It will take infinite time to come back to the mean position, exact mean position. It will take infinite time. So the displacement time curve for critically damped system lies below any of the curves for overdamped systems, definitely. So if the conditions are overdamped, that time whatever the time displacement curve you will get, it will means the time displacement curve for critically damped system lies below that overdamped system. Okay, the motion represented by equation 2 in critically damped system is also aperiodic. Why aperiodic? Because the system is not allowed to move in a forward direction after coming to the mean position. So the total displacement of the system is absorbed in a half cycle itself. So the motion represented by equation 2, that is x, the equation for x, whatever we have seen in the previous slide, it is also aperiodic. The system is non-vibratory, therefore the system is non-vibratory, it is not vibrating further. In this system, once the system is disturbed, it will move back rapidly close to its equilibrium position in shortest possible time. After that, it will take infinite time to come exactly to equilibrium position. In the applications of critical damping are found in hydraulic door closures, the electrical instruments where the displaced body is brought to equilibrium in minimum possible time. Then the third case of our discussion is underdamped vibration or underdamped systems. If the damping factor zeta is less than 1 or damping coefficient C is less than the critical damping coefficient Cc, the system is said to be underdamped. This is what the definition of underdamped system. If the damping factor zeta is less than 1 or the damping coefficient C is less than the critical damping coefficient Cc, the system is said to be underdamped. Then after putting the initial conditions for finding the displacement equation x, we get the equation for x as y into e to the power minus xi into omega n into t into cos of square root of minus 1 minus xi square into omega n into t plus phi 2. This phi 2 is the phase angle or phase difference between the applied force and the displacement of the body, and y is one more constant which we have to define. Okay, so the motion governed by the above equation is of the oscillatory type with the damped natural frequency, that is omega d is equals to square root of 1 minus xi square into omega n into t. If you compare this equation with the displacement equation of SHM, then this value will definitely, you will find this is equal to the omega square or omega n square, which is the frequency of SHM. So if we compare this equation with the x is equals to capital X into cos omega t. If you remember the fundamental equation of motion for SHM, in that equation we will have the x is equals to capital X into cos omega into t. So omega is the frequency. With that we can say phenomena, or we can say principle, we can say that omega value, the this value, that is square root of 1 minus I square into omega n into t, is nothing but the frequency of vibration. Somewhat it is a frequency of vibration. Okay, therefore we can write this as omega d, which is the damped circular natural frequency for the damped vibratory systems, and its value is omega d is equals to square root of 1 minus I square into omega n into t. This equation you have to remember to find the natural frequency of damped vibrations. And an amplitude x into, this is what the amplitude, x or y, you can write anything, an amplitude x into to the power minus I into omega n into t, which decreases in an exponential manner with the increase in time. So I will again I will repeat some part of this slide. Okay, if you see this equation, as we have discussed, that this is what the equation of displacement for the case of underdamped systems or underdamped vibration. And as we have discussed, if we compare this equation with the equation of displacement for the SHM equation, which we have discussed in our 4th or 5th lecture, somewhere we have discussed to find the fundamental equations of vibration, in that case we have discussed. So in that we have seen that small x, which is the displacement of the body from its mean position after certain time, so that x is equals to what we have got, capital X into cos omega t. Okay, so with that terminology, if we compare our this equation with x is equals to capital X into sin omega t or cos omega t, that capital X is nothing but the amplitude of vibration and omega is nothing but the frequency of the vibration. So if we compare that x with this, then we get this, we can say that this part of equation is nothing but the displacement of the or amplitude of the underdamped vibrations or damped vibrations, and this part gives us the value of frequency. But as this is a case of free vibration, so this frequency we can explain as natural frequency, and as this is a case of damped vibration, so we can say that the natural frequency of damped vibration is equals to square root of 1 minus I square into omega n into t. And now, as just I have said, this part of the equation, which is y into e to the power minus I into omega n into t, is nothing but the amplitude of vibration or displacement of vibration. If you put any value of xi is constant, suppose as it is less than 1, suppose 0.8 or 0.5, into omega n, certain value we will have for natural frequency also, and now the only value which will change is t, changing value is t, variable is t. As time increases, then what happens, it will give certain effect, and it is in the multiplication of y. Y is what the initial displacement that you have given. So as the time increases, the value of this x will definitely decreases in each cycle. So that is what the meaning of this, that is an amplitude x into or x into e to the power minus I into omega n into t, which decreases in an exponential manner. Why exponential manner? Because we have e, that is logarithmic base. That's why whatever the amplitude initially you have given, in each cycle it will decrease in exponential manner. Thus the resultant motion is oscillatory, having frequency omega d and decreasing amplitude x into e to the power minus I into omega n into t, which ultimately dies out after some considerable time. Okay, as the name indicates, underdamped system. In both the previous systems, that is our overdamped system and critically damped system, we have said that the motion is aperiodic. Means after giving the initial excitation, system will not perform further oscillations. It will try to come back to mean position only, means it will perform only half cycle. But as this is a case of underdamped vibration, means the damping is less, so the system is allowed to move further. After coming to the mean position, it will move towards another extremity and will perform certain number of oscillations depending upon the time as well as the value of zeta. In each cycle, the amplitude is go on decreasing. Okay, after some considerable time, the total system will come back to the mean position, rest position. So if we plot the time displacement curve for this case, then you can easily understand that system is performing certain number of cycles. In each cycle, if you mark the displacement of the body from mean position, then you can definitely understand, you can easily observe that in each cycle the displacement is go on decreasing. And if you draw the line joining the apex of all these crests, then you will get that it is a straight line, and the this we can say curve, we can explain as exponential curve, and we can say that the displacement in underdamped vibrations is decreasing exponentially in each cycle. Therefore, the natural frequency of damped vibration can be given as omega d is equals to square root of 1 minus xi square into omega n, and therefore the natural frequency of damped vibration omega d is always less than the natural frequency of undamped vibrations. Omega n is what we have. This omega n is the natural frequency of undamped vibrations, and omega d is what we have. It is the natural frequency of damped vibration. And what is the relation between them is omega d is equals to square root of 1 minus I square into omega n. Therefore, we can easily understand from this equation that the natural frequency of damped vibration is always less than the natural frequency of undamped vibrations. Thank you.